studying the rate of reaction. In the last video also we have studied about this, and this video also we will discuss on this. Okay, the rates of chemical reactions are affected by following factors: molecular collision, activation energy, nature of the reactants, concentration of the reactants, temperature, and the catalyst. Okay, catalyst also can increase the rate of reaction. Okay, so these are now. So let's discuss about the molecular collision, right? More collision, more is the reaction. So effective two species A and B, they may be molecules or ions or react. They must collide, right? So to become the reaction, they must collide. So it is possible to calculate how many collisions will take place between A and B in a given period of time. So, and such calculations indicate that the rate at which A and B collides is far greater than that of the rate at which they react. Okay. The conclusion is that the most collision do not result in a reaction. Okay. Only the effective collision can result in the reaction. So not all the collisions can produce the reaction. So only the effective collision can produce the reaction. So that's why the number of the effective collision is most important. So there are two main reasons why some collisions are effective and others are not: activation energy and the relative orientation of the colliding particles. So some collisions just passed through it. Some collisions had the complete collision, so that can produce the product from the reactant. So not all the collisions are effective. Only the effective collisions can be responsible for the reactant converting into the product. Okay, so now let's discuss about that's why the activation energy. So those collisions cross the activation energy can reproduce the product. Okay, so the collision which can overcome the activation energy can they are said to be the effective collision. So the activation energy, so the new terminology, activation energy. What is activation energy? The minimum energy required for a reaction to take place. What is the minimum energy that required to happen the reaction? So to be the collision, and collision means particles should collide. That means the particle should be in the kinetic energy, right? So kinetic energy means you need some certain amount of the energy to initiate the reaction. Whether it is spontaneous or non-spontaneous, you need some certain amount of the energy to initiate the reaction. Okay, that the minimum amount of that energy is said to be the activation energy. Okay, so in most chemical reaction, one or more covalent bond must be broken, right? The chemical reaction means either bond should be broken or bond should be the formation, right? So reactant will break the bonds, and in the product it will reform the another type of the bond, another covalent bond. So however, there are another reaction also, like the Ch7 trans isomer, for example, right? One structure to other structure, there are no any bond breaking, bond forming, only the structural change. That is also a chemical reaction. But generally in the most chemical reactions you are breaking down the bond. So let's take one very easy example to understand. So hydrochloric acid base reaction plus NaOH, very simple reaction. Okay, so this is acid and it will give you NaCl, sodium chloride, plus H2O, right? Look at that, what covalent bond are forming here and what are breaking. HCl, there is a bond between hydrogen and chlorine, plus sodium hydroxide, sodium oxygen hydrogen, right? Sodium hydroxide, that is. So this is the bond are here. Now new bond is forming here, that's the ionic, right? Na plus Cl minus, that's the ionic bond. And the H2O is oxygen, water, oxygen and hydrogen. So this bond is breaking, right? This bond is no more. This bond is breaking, this bond is breaking. But now this bond and this covalent bond is forming. So some bond are breaking and some are forming during the chemical reaction. So to break the bond, you need some energy, or to form the bond also you have to consume the energy or you have to produce the energy. So this energy comes from the collision between A and B. What energy you require? The covalent bond must be broken, and the energy is required for this to happen. To either the bond should break or form, you need the energy. That energy comes from the collision. And how does the collision forms? Because collision is forms if they have the kinetic energy. If the collision energy is large, there is sufficient energy to break the necessary bonds and the reaction takes place. So the collision energy is sufficient enough so that because the collision can be very weak collision also, very strong impact also means the collision also, right? If the collision energy is large enough to break the bond, then reaction can happen. Okay. If the collision energy is too small, no reaction. Yes, it's the collision, but the energy is too small, there is no reaction. Okay. So now let's see the molecular collision. Okay. So the colliding particle must be properly oriented. For example, to be the effective collision between water and the hydrochloric acid molecules, the oxygen of H2O must collide with the hydrogen of HCl so that the new OH bond can form. So collision can have, first of all, they have sufficient impact, right? Sufficient collision, sufficient energy. The collision with the sufficient energy. That is one. Other is the orientation is also important, right? For example, look at that, water and hydrochloric acid. In this case, you can have this collision, you can have the new product, right? H3O plus Cl minus. You know, the acid hydration means the acid and water reaction it gives you the hydronium ion, right? So, but if this type of the collision, there is no reaction then because of the orientation, right? However, it is the energy of the collision is the sufficient, but oxygen and the chlorine are colliding, but at that situation you don't have the product. So the not only the energy, the orientation also important. So the proper orientation also necessary to give the product due to the collision. Okay. So this is one example. So now let's see, we will study here very important other phenomena, that is the energy diagram. Okay. So energy diagram tells you that what is the energy, activation energy, and whether it is endothermic or exothermic, etc. Okay. Now consider the reaction. This is hydrogen plus nitrogen gives you the ammonia. In this reaction, 6 covalent bonds are broken. Of course, 3 are this plus 3 H, right? So there are 3 hydrogens. One hydrogen molecule, other hydrogen molecule, other hydrogen molecule. Plus nitrogen has 3 bonds, right? Nitrogen has 3 bonds. And that whole gives you 2 ammonia. One ammonia and other ammonia, right? There are 2 ammonia. So how many bonds are breaking? This breaking, this breaking, this breaking, this breaking, this breaking. 6 bonds are breaking. And how many are forming? 1, 2, 3, 4, 5, 6. Yes, in this case, 3 are breaking and 3 are forming. Okay. So breaking the bond requires energy, and forming a bond release energy. Okay. When the bond breaks, always, if the bond breaks, it requires the energy, because you have to break that. You have to take 2 molecules apart from each other, right? Bond breaking means, for example, hydrogen molecule. If you want to break this, means you have to take this hydrogen apart from this, apart from this. For example, hydrogen, and you have to take this hydrogen that much farther away. For this, you need the energy. You have to give the energy. Hydrogen, you have to give energy here and that can. So for the bond breaking, you need the energy. You require the energy. Okay. But the forming the bond releases the energy. For example, forming the bond means this hydrogen is here, this hydrogen is here. They have certain kinetic energy. So they come together and forms this one. When bond forms, it releases the energy. When bond breaks, it consumes the energy. So bond forming is, that's why it releases energy, that's why it is exothermic. And bond breaking is endothermic. For bond breaking, you need the energy. For bond forming, is release the energy. So overall is what? Overall reaction energy is what is more, right? If the energy required to break the bond is more, it will be endothermic. You will need the energy. It will consume the energy to happen the reaction. If the bond forming is, if the formation of the bond means releasing the energy, and that is more than the bond breaking, then it will be exothermic. Then you have that. Okay. So reaction is exothermic. Okay. Here is in this case. In this reaction, the energy released in the making 6 new bond is greater than the energy required to break the 6 original bond. That is why it is a exothermic reaction. So that's the reason. So total energy is something is breaking, how much energy you required for that. Something is forming, how much energy it released that. So remember that bond breaking, it is consumes the energy. And bond forming release the energy. Okay. So bond forming, and if bond formation energy is more than bond breaking energy, it is exothermic, right? Because you have releasing is more and consuming is less. That's why you will produce the energy due to that reaction. Opposite way, it will be the endothermic. So now let's say this very important diagram for the energy diagram. Okay. Let's say delta H reaction, heat of reaction, that is denoted by delta H enthalpy, sometimes it is also enthalpy of reaction also, is equals to forward E activation forward minus energy activation reverse. So what is that? Look at that here. So let's see that. This is the energy of the reactant, right? Let's see, this is energy. Here, let's say this is the energy of the reactant. Now let's say like this, okay? Now this is 5 kilojoule. This is the energy of the reactant. Reactant has also energy, right? And when they come together, they increase energy, and one maximum point will forms and then release the energy, decrease. Okay. So now you can have this product. This is the product energy and this is the reactant energy. See, reactant energy is here. This much is here. But the product energy is this. Right? In this case, product minus reactant will be negative. Okay, this is the exothermic. Look at exothermic this is. Okay. So energy product is this much. Forward energy is this much. Okay, EA forward is this much, EA backward is this much. This is wrong written here. So forward is this much and backward is this much. So this is reverse. Okay, this is reverse. This is reverse. Okay. So now look at that. This hill, this top hill, this much energy, this top hill maximum, this value is said to be the activation energy. Okay. So now energy decreases and this is the energy of the product. So energy of the product is this one. That's why total energy is how much? Energy of the product minus energy of the reactant. Reactant energy is this value. Product energy is this value. This is the product energy value. This is the reactant energy. That's why difference is your energy of the reaction. So product minus reactant is your energy of the reaction. This is energy of reaction and this is the exothermic. So activation energy, this activation energy means you have to cross the barrier. You have to cross the barrier. So now let me, for example, let's say this example. Okay, what is the activation energy in this case? Okay, let's say this is 10, 15. Okay, Now 0, let's say this is 5. What is the activation energy? This is the forward activation rate. So that's why this is 15 minus 10 is 5. Let's say joule, okay. 5 joule is the activation energy. The height of this hill is the activation energy. Okay. So what is the backward activation energy? Backward activation energy is from here to here. 15 minus 5 is what? 10. 10 joule is the backward activation energy. And what is the reaction, the heat of the reaction? This minus this means 10 minus 5 is 5. 5 joule is the heat of reaction. So which reaction is more feasible? Look at that. Reaction from right to the left to right or right to left. Means left to right you have to start your journey from here. You will go here, go here, go here, go here, and then directly you come down here. You have only to cross this much hill. You have to only to climb this much hill for the forward reaction. But the backward reaction, if you start from your journey from here, you have to cross this much hill, right? So in the backward you have to cross this much height. You have to climb this much height. But the forward you have to climb only this much. That's why which is better? Which is easier? The forward is easier. So, and the forward is easier means the activation energy of the forward is less than activation energy of the backward. So in this case it is exothermic. This is exothermic. Or this is the energy of the reactant, and this is the energy of product. So energy of the reactant is, or you can say that this is smaller, right? This is 5. Then the energy of the product by the sign, not by the magnitude. Okay, magnitude is this. So in that situation, forward minus backward will be negative, right? So this is that much and forward is that much. Forward is 15 minus 10 is 5 and backward is 10 minus, backward is how much? The 15 minus 5 is 10. 5 minus 10 is negative 5. So its sign is that's why negative. So this is said to be the exothermic reaction. So but in this case look at that. Energy of the reactant is this. Energy of the product is more than the energy of the reactant, right? Energy of the reactant is this much, this value, but the energy of the product is this value. So energy of the reactant is suppose 5, this is 10, right? Energy of the reactant is less than energy of the product. That is the endothermic reaction. Okay. So what is the energy of the reaction? This product minus reactant. That is the energy. And this is the positive value. You see that. Previously it is a negative value because it is less than that. That's why it is a negative value. Now it is a positive value. So this is the endothermic reaction. So these diagrams are said to be the energy diagram. Look at that. These two are reaction, H2O plus HCl. This is your transition state. In that case, it is now ready to give you the product, and this is your product. Product has this energy, reactant has this energy, and transition state is this. Top hill is the transition state. So that's the energy diagram. Now let's see again. So the same thing previously what we studied, we are repeating here. E forward, activation energy for forward reaction. EB rev means activation energy of the backward reaction, right? This is the forward and this is the backward, and this is the product, this is the exothermic reaction. We have to see that. Now let's see one example, and in that example we will plot here. Okay, what is the energy of the reaction in which the forward reaction energy is A forward is equals to 125 per kilojoule per mole, and the backward activation energy is 341 kilojoule per mole. Determine if the reaction is endothermic or exothermic. So the reaction is, so 2NO2 gives you 2NO plus O2. Okay, so now let's first of all make the graph. E forward is 125. Now we don't know what is that, but this is 125. Okay guys, so this value is 125. So that's why this is the 125. Now after this peak, it go down, and then this is your this one, and now the backward is how much? 341, right? That's why it should go down. This is how much? 341, and this is how much? 125. Yes, this is exothermic, right? Because this kind of graph is exothermic, right? The reactant energy, this is the product energy, right? Reactant energy is greater in sign or less in magnitude than the product energy. That's why this is the exothermic reaction. But you can find out delta H reaction reaction. If delta H is negative, then it is what? Exothermic. If delta is positive, it is endothermic. Delta H equals to EA forward formula. Remember that the formula forward FWD minus EA backward. Backward is denoted by reverse, right? And EA forward is how much? 125, right? And the activation energy of backward is 314, 341, and that is minus 216. Oh, okay, it is negative. Enthalpy is negative. It means it is exothermic. So this is the exothermic reaction. So now let's see. This is the other example. Okay, this is the endothermic, right? The reaction, the energy of the reactant is less than energy of the reverse or energy of the product. Yes, of course, this is the endothermic. So now let's see. Now plug in every value here. E forward is 58. EA forward is 58. This one, right? And the backward is 50. Okay, reaction is 55.3. It's given the different way. Reaction, heat of reaction is 55. Heat of reaction positive means it is endothermic, right? So now what is say that the activation energy for decomposition reaction is this one. This is the activation reaction is 58.6. So decomposition of nitrogen to the nitrogen dioxide is a reversible reaction. The activation energy for the decomposition is this much. Okay. Now this two N2O4 plus this is its energy gives you 2NO2, right? It is, of course, it is endothermic. Okay, 2NO2. So given delta H reaction is equals to given how much? 55.3. It is a positive, right? Kilojoule. It is given. So this is positive. That's why it is endothermic. Okay. Now EA forward is equals to how much given? 58.6 kilojoule. So we have to find out E backward, right? So delta H reaction is equals to EA FWD forward minus EA backward, right? So EA forward is how much? 58.6 minus, we don't know what is that, EA reversible, and that is equals to how much given? 55.3. If you solve for that, backward is equals to EA reverse or EA backward is equals to 3.3 kilojoule. How much small? Look at that. This is 3.3 kilojoule. Very small that is. Okay. So now what will be the figure? Figure is initial is this, right? And then increases, and it will go here and then go like that, because this is 58, right? This is 58. Okay. This is 58, and the rate of reaction is this one, this to this, and that is equals to 55.3. And what is the rate of reaction? This one, this guy is how much we get? 3.3 kilojoule, right? So very small, very weak, right? Very small energy. It is the rate of reaction, but this is a positive. That's why it is the delta heat of reaction is that much, right? And so 55.3. And reversible is that one. Reversible is 3.3. Delta, sorry, EA reversible is that one. So now this one, that's why this is the endothermic reaction. Now let's see the transition state. Okay, we discuss later on the transition state, right? So what happened is, this is your graph, right? Here was HCl plus H2O, right? So HCl plus H2O, here you have to make H3O, right? Cl H H2O. This is your transition state. Transition state means neither completely these broken nor completely the attached. That's the transition, and its energy is maximum. Remember that. Which has the maximum energy during the reaction? Transition state has the maximum, because transition state you get the here. So this looks like that. You see that? Okay, iodine is here. You see, neither this bond is completely forming nor this bond is completely broken. So this scenario are hypothetical. Okay, however, these has the maximum energy, and that is the transition state. So let's see that the transition is a maximum on an energy diagram. Where the maximum on the energy diagram, that is the transition state. Okay, that's the transition state, maximum on the energy diagram. So now reaction energy diagram, for example, this picture, right? See, so the reaction is NaOCl plus NaOCl gives you to nitrous oxide plus chlorine, right, gas. So what is happening? Look at that. This is the structure forms. Very interesting, right? This is, look at that. The structure NaOCl is like that. Okay, NaOCl gives you 2NO plus Cl2. These are clear, right? That is what? NaOCl, ONCl, right? So that is okay. That is a NaOCl. Think like that. Okay, NO is N like that, right? So N like that. So okay, and the plus Cl2, Cl like that, or this may be NOCl, right? Like that. So these are the very clear molecules, right? But during the reaction they come close together. The concept is come close together and neither completely broken nor completely forming. And now you have a strange type of the scenario will be there. NaCl is still, now Cl is going apart. Okay, previously Cl is close, chlorine is close to nitrogen in NaCl. Now it's a little bit farther, but that chlorine is not completely attached yet. Okay, Cl and N. See, these two chlorines want to come together and form, but they are still need to be separated. This type of the scenario, because one NaOCl, this is another NaOCl, right? Cl has to come together because you have to make the chlorine gas, right? See, you have to make the chlorine gas. So you have to make the chlorine gas. Look at that here. You have to make the chlorine gas. That's why Cl should come together. So this scenario, this situation is said to be the transition state. So the transition state are, that's why always, whether this is an exothermic, endothermic reaction, this is endothermic reactions, its transition state has the maximum energy, and endothermic, exothermic reaction also, the transition state has maximum energy. So now this is the reaction N plus O3, this is the NO plus O3, right? This type of the strange situation will happen. This oxygen should want to break and attach with the nitrogen to give the nitrogen dioxide, right? So, but this is not completely broken state, neither completely joined nor complete. This is the transition state. Little bits after some time it want to give you the product, but right now it is not completely dissociates. Okay, so this type of the are said to be the transition stage. Okay, in this way we have completed this video, and we will go further in the next videos. And thank you so much, and see you next video.